for those that were here last class, what is this up on the projector? Okay, something about a z-score. Anything else? Okay, so we got a curve. There's some area under the curve. What is the area under the curve?
1.
Well, at most it's 1.
The percentage of the data set or something like that.
Okay, so one way that we can think about it is the proportion of the data. If we think of the area under the curve as 1, that is also has 100%. Right? 1 is 100%. So we can think about this as the percentage or the proportion of our data as it's distributed. Okay. So what I handed out last class and what I gave those of you who weren't here on Friday is this chart. And it allows you to, once you have a z-score, to figure out what that area is. When you're encountered a z-table like this, always pay attention to how they draw the figure, because that's really important, because it allows you to understand what these numbers in here represent. So if we have a z-score of 0.00, how much of the data is to the left or less than our z-score? Half. Why do you say half, Joey? Because it says 0.5. So this part of the table right here, this is called the field. This is the field of the table. So in the field of the table, under 0.00, it tells us that half of the data is to the left, remember our left as we're looking at it, of the z-score, which is less than. Okay. So what I want to do today is I want to practice this. Because again, if we can just get through the routine of it so that it's bucket on the floor, so that you all know how to do this, then I can make this a little bit more complicated. And the only thing that I'm going to change is what the values mean. I'm not going to change how the curve works or anything like that. So this is the skill we need to master, and it's reading a table. And if we can do that, then I can do a whole bunch of fun stuff with this z-score thing. Okay? So for those of you who missed last class, or who had a really awesome weekend and can't remember a lot of Friday, let's play with this a little bit. Here we have an equation that's wrong. Nobody ever noticed that? Actually, it's not wrong. It's just not the one I want to show you. All right. This is what I want to show you. Okay. Well, this is where we started. All right. Z-score equation. To find z, we need to know x, the value of the data we're looking at that's interesting. So that could be an individual's shoe size. It could be your test score on a test. Okay. Mu, little curly m, is the mean. Now I wrote it this way because it's meant to be the population mean. It's meant to be the mean of our entire sample. So you find the difference. And then you divide that by the standard deviation, little sigma. That gives you the z-score. We look up the z-score. Little note about computations after grading your homeworks. Let's all agree that our homeworks and anything we turn in are going to have 2 digits after the decimal point. So if you're rounding, round to the hundredths. Let's agree on that, because that's what our z-table is going to use. So let's just, again, carry that practice forward. Now, because this is a math equation, we can play around with this a little bit. What if we needed to find some of the other values? Because in all the homeworks, I'm going to give you these three things, right? I'm going to give you x, I'm going to give you mu, and I'm going to give you sigma. But what if we needed to work backwards? And instead of finding the z-score for a known quantity, what if we had an unknown? What if we needed to change this equation around? Well, we can get to this. We can also rearrange this around so that we can find out maybe what our x needs to be. So maybe we want to know what the specific value of x is in between our x-axes to maybe find a percentage or something like that. All right. So there are ways in which we can take that one equation and move it around a little bit. So let's start with a very easy example. Let's say we have a data set that has a mean of 100 and a sigma of 15. This should sound familiar because this is the IQ example we did last class. I'll draw my normal curve. Let's look for what proportion of scores is between, say, 100 and 120. Okay, now I've got the word proportion up there. I'm not actually looking for a proportion. What am I looking for? It starts with the letter A. All right, I'm looking for the area of the curve that's between 100 and 120. What should I do first? For what? Why 115? Okay, so I'm going to use those in the equation. Actually, there's one other thing that I should do first. Who thinks I should do something else first? Everybody's just like, I don't know what the hell's going on. Do something. I don't care. Anything, so I don't have to sit here and listen to you. Jake, what would you do first?
You got to do something with 100, 120.
What do I have to do that for?
So you can figure out what you're looking for.
Okay. So where should I put the 100?
Or like on a chart or like on a...
No, like on the curvy thing.
Oh, it's like 100. So was it 100 the average you had?
Wasn't it? Yes, it was.
So you put 100 down the middle.
Okay, so that's the first thing I should do, right?
Yep.
Just put 100 down the middle.
And then
Where do I put 120?
every to the right of that, you got to figure out what the standard deviation is.
Well, let's just put it here. You know why? Because this doesn't have to be to scale. But why is it smart to put the 100 in the middle? Okay, it's the average. Anybody already know something else I can probably put up here? Anybody know already what the area of this part of the curve is? All right, so from here to here, I know that it's half. Why do I know that? Well, it's very simple. I know that my equation, z equals x minus m over sigma, z equals 100 minus 100 over 15. So my z is 0 divided by 15, which we know is 0. Okay. So when your x and your mean are the same value, you know that's a half. That will happen regardless of what the standard deviation is. Okay? So with one of the values that you're interested in finding the x-score is your mean, you already know what the z-score is. It's 0. And a z-score is 0. It's the midpoint. It's half the area of the curve. So this area equals 0.5000. Okay? Now we got to find what? What's the next step? You guys only really know how to do one thing, so just tell me how we do that one thing, and that'll by default be the next step. What do we got to find now? The z-score of 120. Okay, so how do we do that? Well, we know this. Z equals 120 minus 100 over 15. Z equals 20 divided by 15. Z equals 1.33. Because it's 1 1/3. Go ahead, get your phones out, check my math. Pretty sure it's right. Smart. Wrote it down. Okay. So now what do? I got a z-score of 1.33. What's next? Use the chart to find that area. Yes, keep them. So let's go to the chart. 1.33. 1.3. Oh, that's going to look messy. It's this one here, right? So somebody quick, remember this. 1.33 is 0.9082. Right? 9082. 9082. Okay. What does that mean?
That means that 0.9082% of all people fall below 120.
Okay. So now how do I figure out the gap between them? No.
Yeah.
No.
You subtract half from 0.9082.
Yes. What did you say?
He meant like the 1.
Yeah, I would subtract
He said subtract 1 from 1. No.
Subtract
I'm not going to subtract 1 from 1.
0.9028 from 1.
I'm going to subtract 0.9082 from 0.5000.4082. What's that mean? Not yet, you don't.
About 40% of all people fall between 100 and 120.
All right. So our answer, let's go with green. Spartans kicked ass this weekend. Yes, they did. They led up. That area, right, that space between 100 and 120 is equal to 0.4082. Agreed? Now you can ask a question. Why did I use what? Okay, so let's look at the chart one more time. And let's see if I can get this highlighter to actually work. Go away. I wanted a z-score of 1.33, right? So the way that this is arranged is this first column here gives me the first two of those digits. So it gives me the 1.3. All right. But now I need the 0.3. So this is 1.30, this is 1.31, this is 1.32, this last one is 1.33. It's just a way of putting all of the numbers so that you can sort of see them all in one spot. Okay? So the first column is the z-score, and then the next 10 columns are all the hundredths of the z-score. Okay. We all agreed that this is the right answer. We all understand. So the proportion of scores between 100 and 120 is 0.4082. Or if you want to change that word from proportion to percentage, what percentage of scores are between 100 and 120? The answer is 40.82%. Proportion and percentages, it just depends on where you put the decimal point. Okay. Let's do another one. Same setup. Mean 100. Standard deviation 15. Tell me the area between 95 and 98. And go. I'll let you work on it for a minute. All right, let's finish up if you're still working. If you've given up, we got you. All right, what's the first thing I do? Okay. A particular reason you chose 98 first? Okay. How do I do that? X is 98 minus 100 divided by sigma, which was 15 still. Z equals, -2. Shenanigans. Divided by 15. That equals 0.33 negative. Oh, I'm going to have to think about that for a minute. Let's do the other one. Z equals 95. Or actually, that's a 1, sorry. See, Jake wanted to do things out of order. Z equals -5 over 15, which is a -1/3, which is a -0.33. Okay. I got 2 z-scores. Now what? Okay. So 0.33 is what? Yeah, turn your page over. Oh, small detail. All right. -0.33. I'll give you. Here it is. 0.330, 31, 32, 33. 3707. 3707, 3707, 3707. Okay. What's the other one?
4483.
Okay. Now what do I do? Yes. What from what?
Bigger one from the small. Smaller one from the bigger one.
You sure? Okay. So I'm going to take that number, subtract that number. Okay. What's the answer?
0776. No, zeros.
0.0776. So, what's that mean?
7.76% is between 95 and 98.
Exactly. Okay. Does that make sense? Who got it wrong and why do you think you got it wrong? Did everybody get it right? No? Didn't finish? We on the right track? No. Why not? It's not confusing. It's bucket on the floor. I've given you one equation, right? No, that, don't be quitters. Right? I've given you one equation. All you have to do is apply the things you know in that equation, do some math, get an answer. Yeah, okay, I get reading the chart can be tricky at first. But it's just at first. All right. So what are we trying to do? We're trying to find how many cases, how many observations are between two numbers. You take the x, and all we're doing is converting it to z-scores. So down here, this is our z-axis. Right? Well, it's not. It's the x-axis with our z values. And we try to find which z represents 98, which z represents 95, and how much is the space in between them. That's all we're doing. Let's do this one more way. I'm going to change the standard deviation on you, though. I want to know, that one's really ugly. I want to know the 95% in the middle. Which values of x create 95% in the middle? Okay, I'll give you the mean. Mean is 100. And let's change sigma to 5. I'm not sure why I did that, but I did that. So what are we trying to do now to answer this question? Because I haven't given you x, right? I haven't said 95 and 98. We need to find x. So we're going to use a different formula. We're going to use the exact same formula, but we've solved this formula for x. So what does it look like now, Joey?
X equals z times beta plus the mean.
Plus the mean?
That's what I wrote down.
Okay.
Is that
Subtract. Yeah, that's what it is. Because I got a negative, which means once I solve this thing, right, by multiplying by q over, or excuse me, over sigma over 1, I get z sigma equals x minus m, and then I plus m to get the m's to cancel out and carry the plus m over here. Yeah, math. Okay? So, all right, we have that. Now what do we do? What numbers do we know? Okay, it's sigma, but so we know that this is plus 100. Okay, and sigma is 5. Okay, now what do we do? We know our final answer is going to be x. What's the one thing we don't know? How can we find z? Okay, so let's think about this for a second. We need to find these z-scores, but we already know the area, right? Usually, in the previous examples, the area was the thing we were trying to find. Now, we're not looking for the area anymore. We're given the area. Well, where does the area go so that we can find the z? We look on the table. Now, I want you to just look at the picture for a second. There's one little detail that I left out. What's the z-score at the mean? Well, that is the mean, but what's the z-score at the mean, Jake? 0. So if I'm looking for a z-score over here and a z-score over here, one of them is going to be what? One of them is going to be positive and one of them is going to be negative. Okay. Which one do you want to look for first? The positive one or the negative one? Let's look for the positive one. Okay. So I know that that z is going to be towards the end. So I'm going to look at my positive chart. All right. Now what am I looking for? I'm looking in the field. What am I looking for? What number am I looking for in the chart? No. It's not 95%. Nope, it's not 0.95. Half of what? Which is? You're off a decimal. Now, I've got 95 in the middle. How much is left? Now, what do I have to do with that 0.05? Right, I got to split it in half. So the area that I'm looking for here is 0.0025. Or no, sorry, one too many zeros. Sorry. In this tail, and I'm also looking for the same over here. Now that you know that, where do we start? Why the negative side? Because it's easier. Why, Jake?
Because 0.025 is the value on this chart. It's not on the front.
Yeah. All right. Let's think about this. We got to find the two shaded parts. All right. We've got to find this one here, and we got to find the value that gives us this one here. Well, looking at my tables, the negative side gives me this one. And what's the corresponding z-score for a 0.0250 probability? All right. Tom says it's negative 1.96. Do we agree with Tom? Danny does. Anybody else completely lost? Yes. We'll get there in a minute. Let me keep talking for a while. Hopefully that helped. So, how did we get there? Well, Tom looked at the field for the number representing the area we were looking for. You look, and you're just looking, right? I know that I need 0.02. So I'm looking down through, where did the 0.02s start? It's right around 2.05 in my field. You see that? Negative 2.05 gives me a score of 0.0202. Right? So again, just to highlight, we know we need to find something that looks like this. We know that our numbers need to be 0.02. Not. So here are the 0.02s, right? They start right around here. And I need 0.0250. So I'm just going to keep going. There it is. That's a bingo. Right? So what is the z-score that gives me this area? Well, I'm following it over. It's negative 1.9. And then I'm going to get the last digit by going up, 6. Negative 1.96. Everybody now understand how I got that? We good, Alexis? Okay. Let's go back to our question, though, because I remember trying to get 2 z-scores. How am I going to get this z-score over here? What do you mean get rid of the negative sign, Jake?
You flip the 1.96 to the other side.
Yeah, you can do that. Why?
Because the middle 95% is going to be symmetrical on both sides.
Yeah. That's the easy way to do it. We know that our distribution is symmetrical, right? So if we take that drawing and we fold it up onto it itself, we're going to get the same overlapping 0.0250, right? These two parts here are the same. So that's intuitive. That's if you understand. What if you don't understand? Okay? What if you're looking at your table and you notice that the little picture at the top looks like this, which it actually does. Now what are you going to look for in the table for a area to find the z-score? Well, let's think about this for 1 second. How much have we said is in this tail here? How much is right here? 0.0250. How much is over here? 1 minus 0.0250, which is 9.1. oh, excuse me, 0.9750. Yes? Look in the field for a area score of 0.9750. Is it there? What is it? 1.96. Okay? Does everybody see that? Do you see it? How many of you just literally quit on this class? One. All right, I can handle one. Okay. None of this has to do with math. It's just reading a chart, right? 1.96. There's your magic number, right? But you have to understand how it is we're dividing up the area of the curve, okay? We okay? Other than her.
So do we not have to plug it into the equation afterwards? Is that it?
No, you do have to plug it into the equation. But before we do that, are we okay? Because this is just really bucket on the floor. Okay? So x equals 1.96 times 5 plus 100. Somebody do that. It should be 109.8. Now I have to do it one more time, right? Why? Because I'm looking for two values of x, and you've only found one, you idiot. Where's the other one? It's the negative. So I'm going to put a little negative sign right here, and that's going to be 91.2. 91.2, 100, and then this is 109.8. So the middle, 95%, are located between 91.2 and 109.8. Make sense? Make sense? No? Okay. Oh yeah, it's 90.2. Simple math. Okay. One more time. This is our normal curve. This part in here, area. Area under a normal curve is 1. From the beginning to the end. When we're dealing with our normal curves, the numbers that we put on the bottom can change. They can be x's, they can be sigmas, and they can be z's. All we're doing is converting our x's into z's. Why did I put the sigma up there? Because I mentioned that in a whole empirical rule thing, right? A certain percentage, or locate 68%, or plus or minus 1 sigma away. This spot here in the middle is the mean, frequently referred to as mu. Our z-score always has a median of 0. All right. And if we do the whole sigma thing, we can talk about that being 1, 2, 3, negative 1, negative 2, negative 3. All right, that's for the empirical rule. But again, that's not helping us computationally. That's just to help you understand the whole spread thing. And right, the cases. X ranges from our minimum value to our maximum value, and Z ranges from 0 to 4 and back to -4, practically. Okay. So all we're doing is using that equation, Z equals X minus mu divided by sigma, to convert our known values into z-scores. The z-scores are important because it helps us understand the area under the curve, which right now we are just using to represent frequency. Right? We're just using it to represent how many values there are in the data set. I know this is my last minute. I want to show you one thing. Remember Hillary Clinton and that feeling thermometer thing? So here's the data on that, right? 2306 number of observations. The mean, our mu, is 62.9. Our standard deviation, our sigma, is 27.1. That's a pretty big standard deviation, right? So what should our curve look like? It should be wide and short, right? So here's what I did. I said, Stata, go ahead and graph this sucker. Let me see what this data looks like. Well, first of all, the data itself, not distributed normally. Because we got a bunch of people out here in the tails that just hate old Hillary. Cheating Hillary, lying Hillary, crooked Hillary, right? Out here in the tails. And when you impose a normal curve on top of it, given the mean and that standard deviation, right, you can see that it's not exactly a normal distribution. We can still treat it like a normal distribution, though. You know why? Because it's curvy shaped. And really all we have is a good sample out of a very larger population. So even if this sample itself isn't normal, well, who's to say that the whole of all Americans and their feelings towards Hillary aren't normal? Okay. We're going to add a little layer on top of this next class, but if you didn't get it yet, just look at it and try to understand, okay, we're doing a couple of conversions here. We're talking about a curve. The curve represents frequency. Okay, I just need you to get the math at this point.